Static friction and kinetic friction. Static friction acts when an object is not moving. It tries to prevent motion. There's a maximum static friction, the highest value before the object finally breaks free and starts moving. Once the object begins to slide, kinetic friction takes over. When we analyze motion with friction, we're really looking at one of the most important and most overlooked forces in everyday life. Friction is everywhere. It lets cars grip the road, helps you walk without slipping, slows down moving objects, and affects almost every machine ever built. In this video, we're going to break friction down into simple, clear ideas so that by the end, you'll understand exactly how friction interacts with motion, forces, and acceleration. Let's start with the basics. Friction is a force that always acts opposite to motion or attempted motion. If an object is sitting still, friction tries to keep it still. If it's moving, friction tries to slow it down. And the strength of this friction force depends on two things: the surfaces in contact and how strongly they're pressed together. This brings us to one of the most important ideas in this chapter: the coefficient of friction. The coefficient of friction is a number that tells us how grippy two surfaces are. It's not measured in units, it's just a ratio. We compare the amount of friction to the amount of normal force. The normal force is simply how hard the surface pushes back on the object. On a flat surface, the normal force is equal to the object's weight. So the friction force is found by multiplying the coefficient of friction by the normal force. Because it's a ratio, different materials give different values. Rubber on dry asphalt has a high coefficient. This gives cars strong traction. Steel on smooth ice has a very low coefficient. That's why skates glide easily. Even small changes matter. Dry concrete, wet concrete, clean ice, rough ice, they all produce different friction values. Now, friction comes in two types: static friction and kinetic friction. Static friction acts when an object is not moving. It tries to prevent motion. There's a maximum static friction, the highest value before the object finally breaks free and starts moving. Once the object begins to slide, kinetic friction takes over. And kinetic friction is always weaker than maximum static friction. That's why it usually takes more force to get something moving than it does to keep it sliding. This difference shows up everywhere. Think about pushing a heavy dresser across a floor. At first, it feels almost impossible. Static friction is strong. But once it finally starts sliding, keeping it moving feels noticeably easier. The same principle applies to starting a car on a hill, pulling a loaded sled, or trying to loosen a stuck jar lid. In every case, static friction resists the start of motion more than kinetic friction resists continued motion. To apply friction to real physics problems, we combine everything you've learned in this unit: free body diagrams, Newton's laws, acceleration, velocity, and forces. When an object is on a horizontal surface with no vertical acceleration, the normal force equals the weight. That makes finding friction straightforward. If the friction force is the same strength as the applied force, the object moves at constant velocity because the net force is zero. If friction is weaker than the applied force, the object accelerates forward. If friction is stronger, the object stays still. Let's take an example. Imagine a hockey puck sliding across smooth ice and suddenly hitting a rough patch. On smooth ice, the friction force is tiny, barely slowing the puck. But on rough ice, the coefficient of kinetic friction is higher, so the friction force increases. That friction becomes the net backward force, causing the puck to decelerate. Using friction equals the coefficient of kinetic friction times the normal force, and applying Newton's second law, we can calculate the puck's acceleration. Then, using the kinematics equations, we can find how much the puck slows down over a certain distance. This kind of problem blends dynamics and motion beautifully. Another example: consider a moving truck skidding on dry asphalt. When the brakes lock, the tires slide, so kinetic friction takes over. Rubber on dry asphalt has a coefficient of kinetic friction around 1.07, which produces a large friction force, large enough to stop a heavy vehicle quickly. But on wet asphalt, the coefficient drops. On ice, it becomes extremely small. That's why stopping distances increase dramatically in bad weather, and why modern cars use anti-lock braking systems to maintain the highest friction possible. These ideas also explain the physics behind road design, tire engineering, sports equipment, and even joints in the human body. Engineers try to reduce friction where it wastes energy, using ball bearings, lubrication, and smooth surfaces, and increase friction where grip and control matter most, like running shoes, tires, or climbing gear. Understanding friction helps you understand why machines wear out, why brakes heat up, and why even tiny changes in surface conditions make a big difference in motion. So when we analyze motion with friction, we're not just solving equations. We're describing one of the most fundamental interactions in nature, one that shapes how objects move in the real world. If you found this helpful, don't forget to like and subscribe to support more educational videos just like this.